So here's the fundamental question that I'd like to focus on for a few minutes. Do we need so many species? This kind of gets at the core of a lot of the discussions that we have, the assumption that, well, we need these species. And many of the kind of more common arguments that we see in favour of conserving biodiversity and endangered species revolve around this notion that the assumption that more diverse ecosystems, those with more species, function better and therefore provide more services and more benefits to us. But really, I guess what we want to do is ask, is it really the case that maintaining a diverse set of different life forms or different species really results in systems that function better? Right, so a bunch of really long-running experiments. This is perhaps the most famous of all of them, the Cedar Creek experiments out in Minnesota, in the US. You see the kind of scale of these experiments. These are all different. This is a grassland with different patches here. I don't know the exact dimensions, but you can get an impression, this is a pretty big scale kind of ecological experiment where they've got different treatments and they've basically planted different combinations of species. So you draw, you draw in a plot and you draw from the main functional group. So you'd have some legumes, you'd have some grasses, some woody plants, some herbivores, grasshoppers, predators like spiders, decomposers like beetles, and you then study how over a period of time those plots functioned by measuring certain things. And the classic things that are measured are biomass production, so just what's the overall productivity in this plot, in a particular plot, and decomposition rate. So how fast does, say, leaf litter, how fast do things decompose? And what do we find? Well, the message is really quite clear that there is generally a positive relationship between the number of species and ecosystem functioning. So plots that have more species tend to decompose dead organic matter quicker and tend to have higher productivity. There's a general relationship, so that's always shown with this dotted line here. Whatever your measure of ecosystem function is, if you have less species, you tend to get lower ecosystem functioning. More species, you tend to get higher ecosystem functioning. So all very well so far. The data seems to support our instinct, in effect. And that kind of underlies one of the analogies that you may have seen talked about in popular kind of outreach, if you like, is this idea of the tapestry of life. So this is just one framing, but it's worth bearing in mind. So this is the idea of the function and beauty of this tapestry of life. So the tapestry being all the interconnections between all the diversity of life on the planet is slightly diminished with each removal of each thread. If too many threads are pulled, the tapestry will begin to look worn and may look or may tear. So it's kind of poetic. It's a nice analogy, and it provides us justification, kind of if you think about a utilitarian framing of this, to conserve diversity. Loss of a species, however rare or unremarkable, will result in poorer function and therefore less benefits to people. That's the framing that we usually come across. Think about utilitarian versus intrinsic value of species. So if the intrinsic value, if it's a rare species, well, it has intrinsic value, so therefore we can value it. From a more utilitarian framing, we need to make this link that species is providing something for human well-being. And with this framing, then that's absolutely the case, because every species is vital. We have this tapestry, this interconnection, that means if you start pulling threads, if you start losing species, then function is going to decline. Benefits will ultimately decline. So it's a nice analogy, but it isn't quite right when we dig into the science. As ever, things are a bit more complicated. What we need to do is think a bit more about the mechanisms that underpin this positive relationship between biodiversity and ecosystem function. So this is where we really need to start thinking not just about species diversity, but about functional diversity, which is, of course, what we've been building up to. So this again comes back to some of Drew's discussion about niches. Because one of the reasons that ecosystems that contain more species tend to function better is that different species working together are more able to make use of the available resources. So this idea that different species fulfill different roles in the ecosystem. But therefore the key is not necessarily to have more species or to have lots of species, but to have lots of different functions. And this basically occurs by two mechanisms: complementarity, that you might have come across before, and facilitation. So complementarity is this idea that basically species complement one another. They have different niches, they complement one another, so they do different jobs within the landscape. So some species will make use of some shaded nook over here, some will prefer it a bit wetter over there, some will do well when it's dry, some will do well when it's wet, some prefer it shaded, some prefer direct sunlight. These are all different niches within the ecosystem. The more species you have, the more niches are filled, the more that they complement each other to make best use as possible of the environmental conditions. So in effect, this division of roles means that a more diverse set of species can pack more activity into an area. So that's the idea of complementarity. Facilitation is the other key mechanism by which diversity, if you like, gets better function. So this is the idea, as I said in the name, that species facilitate each other. They help one another by providing resources for each other, like nutrients, food, or shade. So legumes is a good example. A legume in a grassland, these are the plants where their roots contain these rhizobia, the bacteria that turn nitrogen, gaseous nitrogen, in the soil into ammonia, which then releases that for use by other plants. So it's this idea that you have facilitation, you have a group of species or different functions that provide resources for others. So this idea both of complementarity and facilitation require that species fulfill different niches, they exploit those different niches and undertake different jobs in the ecosystem. So the key then is not necessarily to have lots of species, but to have lots of different functions. It's functional diversity that we see as being really important. So here's another analogy that I think is a better analogy than our Tapestry of Life. Some slightly different points, but this is the idea. Suppose you've got a child that's got 4 crayons and wants to draw a landscape. There's clearly a difference between having a pencil case that's got 4 blues in it versus a pencil case that's got a yellow for the sun, a green for the grass, a blue for the sky, etc. They're different functions, if you like. And the same is true of ecosystems. An ecosystem with 4 species that have the same function, say they all pollinate in warm weather, provides less benefits than an ecosystem that has 4 species with very diverse different roles. So you might have a warm weather pollinator, a cool weather pollinator, a decomposer, a nitrogen fixing legume. The species or the ecosystems might have exactly the same species diversity, but very different functional diversity, and the benefits that we will get will be very, very different. So I'm kind of arguing that the species in an ecosystem are kind of like the pencils in our pencil case, with these different functions rather than threads in the tapestry, where each individual thread, each individual species is playing a kind of equal role. So we need to think about not just species, but about functions. That, of course, is not still the full story. It gets a bit more nuanced than that. Turns out that within functional groups, workloads are very unevenly distributed between species. Actually, what you find, generally, I'm talking about general patterns here, is that a small minority of species do most of the work. So this is just one example. You can find your own for pollination. These are data collected. This is one of these big kind of meta-analyses. There are about 1,300 or so different field studies where they basically, each line here is a species ranked from low to high in terms of their contribution value to pollination, and here it's actually quantified in terms of kind of dollar values per hectare of crop. So the key message here is the classic pattern. You've got a few species that are providing an awful lot of function and a long tail of species that are providing relatively little function. So actually, in this data set, which includes over 700 species of pollinating bees, almost 80% of the crop pollination is provided by 2% of the species. 80% of the function is provided by 2% of the species. And those species are the key ones that are most common in the landscape, of course. So by contrast, a lot of these rare species, a lot of which are the ones that are threatened with extinction, we classify them as threatened, are contributing very little, less than 1%. So we have this, we have to look at the science and show that there's a big disparity in the workload in terms of within functional groups which species are doing what. So we get this kind of general pattern. Whatever our kind of function might be, in this case contribution to pollination, we have this ranking from the highest contributors with a long tail of lower contributors, and we see that across different types of ecosystem service. So if we go back to our pencil analogy, it's as if our child is given lots of blue crayons but still is only using one of them or two of them. So a really important consequence of this is that careful management of just a few species can be effective in maintaining ecosystem function. So you don't really need to save every last species. If you're really wanting to manage a system, manage a function, often you can just concentrate on maintaining abundant populations of the big players. And this already happens in the case of pollination, primarily through managing honeybees, and in fact mostly western honeybees. I've got figures here. There are around 2 million commercial honeybee hives in the US, most of which they're basically loaded onto trucks annually and moved around the landscape. So they go from, I can't remember the details, but they go from the almond groves in California when they need the pollination. They go back into the artificial hives, they get put on the back of a trolley of a truck, and they get taken to some other part of the US where there's the blueberry crop or whatever else needs pollinating. So they're literally just managing pollination when it can be afforded, just in this way. About half of the global demand for crop pollination is through managed honeybees. So what that actually means, the kind of flip side of this, is that actually there's quite a lot of redundancy in these systems. If a few species do most of the work, as we're seeing, then from a functional perspective, a lot of the species are rather redundant. We could actually lose a lot of them without having a big impact on functioning. So we can plot the number of species, again just conceptually, but this is looking for general patterns, against some measure of ecosystem functioning. So this might be pollination, this might be decomposition, whatever it might be. And we find that as we lose species, there's initially a little decline in function, and it's only when we get to lower numbers, whatever that number might be, but relatively few, that we get the kind of crashing big declines, substantial declines in function. So we have this general relationship. It is not the linear relationship, the kind of, which is the dotted line here. So each loss of a species, whether the first one or the last one, will result in an equally small decline in ecosystem function. That's the kind of Tapestry of Life analogy. But the data don't support that. Truth is, there's a lot of redundancy in biodiversity in ecosystems. So we assume that the loss of individual species will result in fragility. So again, going back to our analogy, it's as if you've got a child's pencil case has got lots of blues, lots of greens, lots of reds, lots of etc. But she only needs one of each colour to draw a landscape. She's only going to draw a landscape using a small number of them. So that's what the data suggests. That's what we have to, how we have to frame our arguments or our thoughts in terms of reasons for conserving biodiversity. Now, again, the flip side of this, the other way to look at this, yes, species might be functionally redundant, but the flip side of this is this idea of resilience. So having lots of species that can play a role means that if one drops out, there are other species that can take over. It's this idea of insurance. So the more diverse systems will be more resilient to change. So if climate change or some other threat in the Anthropocene were to wipe out a common pollinator, then the chance that another species would come in and take over that role is much higher in a more diverse ecosystem. So again, biodiversity provides this kind of insurance. So I'm going to stop with the pencil analogy after this one last point, but to stick with it just for one more moment, our child that's got a really big pencil case that's got lots of blues, lots of greens, etc., is more resilient when one of those breaks, when one of those goes blunt. They've got another one that they can pick up. So we've got all these things with complementarity facilitation leading to this relationship between biodiversity and ecosystem function, which on the one hand leads to redundancy, but on the other hand provides resilience and insurance. So do we need so many species? Well, some species can be lost from ecosystems without having a big impact on functioning, but only to a point, until some limits of resilience, if you like, can be reached. So we've talked a lot throughout this module in terms of kind of extinction risk and proportions of species that might go extinct, and that kind of comes back to this big question: how many or what proportion of species can we lose before we hit this point of impacting on the well-being of humans? So I think at one extreme, like 100%, we can clearly show that we don't need every last species on the planet to provide ecosystem functioning. But at the other extreme, if we lost all the diversity of life on the planet, clearly all these functions that we rely on won't happen. So somewhere in between, say losing 25% of species, 1 million species, both numbers right that we've looked at. Remember, the best conclusion was 1 million species at risk of extinction. So we're in this great unknown, right? Can we lose that many species and still maintain ecosystem function? But this is where the science is at. This is where you need to read and be critical of the debate. Sure, we'll be running a higher risk. People would for sure lament the loss of so many species, but it's by no means certain that such losses will result in catastrophic declines.